lecture, at the end of last lecture, we went over the isothermal expansion of perfect gases. And what we find out is even if through an isothermal expansion, your temperature is not changing, but the heat transfer between your system and surrounding is not zero. All right, so normally you link heat directly to temperature, but in a scenario like isothermal expansion, the heat transfer is not necessarily zero. So today we'll start by looking at an adiabatic process, like a reversible adiabatic process. And our goal here is to find the relationship between temperature and volume for this specific process. And after this example, we'll go over some of the general rules in how to answer questions using your first law of thermodynamics and our definition of heat, work, enthalpy, and heat capacities to understand how these things change in specific system with ideal gases. And let's see if we got a chance to start talking about entropy in chapter 3. All right. So at the beginning, our goal here is to find out how is your T, V related in a reversible adiabatic process in a perfect gas. All right, so like in any thermodynamic question, when you're reading the problem, just ask yourself, what does these terms mean in that statement? For example, when we're saying adiabatic, what it means is it's an adiabatic process, so there's no heat transfer between your system and surrounding. Or if we put it in the form of an equation, what we're saying is dq equals to 0, and your total heat transfer also equals to 0. All right. Likewise, when we're talking about reversible process, again, what it means is we can apply this equation, the work reversible, dREV equals to negative PdV. Or if we're taking the integral of this process, what we end up having is W reversible equals to negative integral PdV. Right. And then we also read it. It is a perfect gas. So for perfect gas, we have several things. We put it on there, right? So naturally, we have PV equals to nRT. And we know that U is only dependent on temperature. H is only dependent on temperature. So you have relationships like du equals to Cv dt and dH equals to Cp dt. So that's these equations we're using here. For ideal gases, it's independent from pressure and volume for enthalpy and internal energy, so it becomes a normal derivative. All right, so what we're doing here is just reading the question, and then let's use the first law of thermodynamics to find the relationship of P and T in any adiabatic processes of a perfect gas. All right, so you can see that, right? Okay. And using our first law of thermodynamics, which you can write out as du equals to dw plus dq, and we can replace some of the things here, right? So for example, we know that dw, that equals to negative pdv, and we know that dq equals to 0 for an adiabatic process. And at the same time, we have du equals to Cv dt. So what we're trying to do here is find the link between temperature and volume for an adiabatic process of a perfect gas. So right now what we're doing is replacing some of the state functions that looks abstract, like internal energy and heat and work, into functions of volume and pressure and temperature. So taking that together, or just moving these terms in there, we have CV dt equals to PdV, which in this case, you can write it out. For ideal gases, P equals to nRT over V. Right, so we can write that out. Negative nRT over V dV, and Q equals to 0. Now let's move the terms. So we have T with its derivative and V with its derivative as well. So this is one of the calculus strategy that we typically use, is you move these dependent with its derivative. So when you take the integral, it becomes straightforward in how that integral takes place. So after we move the terms, we have CV divided by T dt equals to negative nR over V dV. Right. And now it becomes obvious you can take the integral on both ends. So we have from T1 to T2, CV over T dt equals to, we can move N and R outside from my integral because both terms stay constant. NR, V1, V2, 1 over V dV. All right. And now it just becomes a pretty straightforward calculus problem. That's what I mean by saying this class uses calculus, but not in an extremely difficult way. So in this case, on the left-hand side, if we assume CV is a constant for ideal gases, then we can easily solve that integral to be CV times ln natural log T2 over T1. And on the right-hand side, we can solve that as well. This one is just nR and ln V2 over V1 with that negative in front. And that's the same as nR ln V1 over V2. All right, then that relationship is within the logarithm, because in the logarithm it's V2 over V1. Effectively, what we mean is nR ln V2 minus ln V1. And you take that negative inside that bracket and you have this relationship. Just a quick refreshment on your logarithm calculus. So with that in hand, what we have on the left-hand side, we have this, that's the wrong color. We have this expression. On the right-hand side, we have this expression. And they're equal to each other because of our first law of thermodynamics. So what we have is CV ln T2 over T1 equals to nR ln V1 over V2. Or if you can write it out in a more straightforward way, you have T2 over T1 equals to V1 over V2 to the power of nR over CV. That's for perfect gas, adiabatic process, and constant CV. So just keep in mind, every time after derivation, we always put what are the hypotheses and what are the thermodynamic process we're talking about in this process. And reversible, yeah. Okay. Any questions before we move on? We will be using this equation, so I'm just going to add it to my equation sheet here. So that's T2 over T1 equals to V1 over V2 to the power NR over CV. Right. So let me finish one more thing. If you think about this derivation, you'll be like, okay, this looks pretty straightforward. Now, one of the things to keep in mind is using the same kind of logic. If we have different set of state of function, instead of PV equals nRT, are you comfortable doing the same kind of derivation using a different set of the state of function or gas law? That's one question. The second question here is these are the terms, right? Adiabatic, closed system, or constant CV, etc. What if I replace that with a specific scenario? Or like instead of saying adiabatic, we can say, okay, so we have a wall that does not allow heat transfer. So it's the same idea, but you need to understand what's the definition of these terms. Okay, now questions.
How did we assume that CV is constant? Is it just for...
This one is just for perfect gas. We are assuming it is constant. It's in our hypothesis. And that's why we put it here. That's why this one is only true if we have constant CV. Now, if CV is not a constant, we will give it to you. For example, CV is it have power of 2 over temperature, then that equation will become a different one. Any other questions? Okay, sounds good. Now let's move on to a quick summary of our entire chapter 2. So this part will first go over some of the things, like you should instantaneously link when you're reading a problem to a specific equation to use. And then we'll spend some time doing examples on different scenarios and see how to apply those terms and what does those thermodynamic properties actually mean in our physical world. Okay, so let's get started. We went over several thermodynamic processes. So different words will give you different information. The first thing, when we're saying the cyclic process, what we are saying is the initial and final thermodynamic state are the same. All right. So when you have a same initial state and final state, what that tells you, for example, when we're talking about state functions, now a state function, its value is only depend on its initial, on its what state it is. It's called a state function. So for a cyclic process, we have all the state function, change in the state function, like internal energy delta U, enthalpy delta H, volume and temperature, and pressure, all equals to 0. So these are all our state functions we went over so far. All right, we will introduce new state functions, but keep in mind when we have a state function in a cyclic process, the change in that state function always equals to 0. Second one, reversible. So again, the definition of a reversible process is the system is always infinitesimally close to equilibrium. It's super close to equilibrium, but it's not at equilibrium yet. So whenever you see reversible, you should instantaneously write out the dW reversible equals to negative PdV for PV work. Now, there are different types of work, like electric work. Hopefully, we get to talk about electrochemistry, but if not, there are other types of work that can take place. But for PV work, you should instantaneously write out W reversible equals to negative PdV. And in our chapter 3 lecture, we will also went over the reversible heat change, dq reversible. That will equals to temperature times change in entropy, and this we will discuss later. All right. At that reversible heat change and also the entropy change gives you a new definition of temperature, which we call thermodynamic temperature. Nevertheless, that's a reversible process. Now let's talk about isothermal processes. Let's assume we have an ideal gas or perfect gas. What does constant temperature tell us? So if a system is at constant temperature, say an ideal gas system is at constant temperature, what does that tell us? For example, related to internal energy, enthalpy, yes?
It's like, no, delta Q is not zero, right?
Well, delta Q may not be zero, but when we're talking about internal energy and enthalpy, what does that tell us? Yeah. Yeah, so, I mean, yeah, both of them are right? So your delta U, internal energy change, and also your enthalpy change will be zero, because for ideal gas or perfect gas, your internal energy and enthalpy are only dependent on temperature. But no, that's only for like ideal gas and perfect gas. So U is a function of T, H is a function of T. So at constant temperature, delta U equals to 0, delta H equals to 0. Okay. Now, yes?
Can internal energy then equal enthalpy?
Well, in this specific case, yes, but only for ideal gases. Again, if you think about it, when we keep T as a constant at internal for these ideal gases, what we have is PV equals nRT. So when your T is constant, your PV is also a constant, right? So if your delta T is not changing, your delta PV is also not changing. So only for this special case, both of them are 0. But it will be very dangerous to write delta U equals delta H because they just happen to be all 0. All right, and then adiabatic processes. What will you write out when you see something like adiabatic processes? Yes, Q equals to 0 and dQ equals to 0. All right. We went over isothermal, and apparently we also have the isochoric or constant volume processes. So for constant volume processes, the idea here is, well, if we only have PV work, then your work will equals to 0, because your volume is not changing. On your PV diagram, that area below the curve will always be 0 if V is not changing. And at the end, when we have isobaric process, it means we have constant pressure. One of the relationship we have is delta H equals to QP. And we did that derivation in lecture 4. If you're like less familiar with that, just go back and check that derivation. Yes?
Is that Q times P?
No, it's Q subscription P. What it means is that's the heat transfer between your system and surrounding at constant P. All right, at the same time, like for example, if you have QV, that tells you it's the heat transfer between the system and surrounding at constant volume. All right, so these are the quick summary. Again, it looks pretty straightforward when we put it like this, but when you actually go apply it in specific system, the quicker you make that linkage between each of the terms to that expression on equation, the easier it is for you to solve those problems. So let's do some example problems here. If you do not have a blank lecture note with you, take a picture because we will keep going and look at each of these examples. But if you have a textbook with you, that's also fine. That's the 2.45 example in your textbook. So the goal here is to calculate your heat, work, change of internal energy, change of enthalpy. In a closed system, only PV work is done. Whether or not it is reversible, it depends on the specific scenario. We all have a copy of this page somehow open? Okay, so let's get started doing it one by one. First one here, we're talking about a reversible melting, or in more general, phase change at constant temperature and pressure. So the way to think about this, now you can imagine a block of benzene solid that is melting at an equilibrium temperature, at some temperature, which is the melting point for benzene. It's at constant temperature because it's at the melting point. It's at constant pressure, like say the atmosphere. So it's something that you can actually imagine happening in our real world, or you can actually do it in the lab. Now, in these processes, we have several information that we know. For example, we know the density of your benzene solid is larger than the density of your benzene liquid. We also know the heat of melting is larger than 0, or it means throughout the melting processes, your benzene solid is absorbing heat from the surroundings, right? So that's what a positive Q tells you. So in this process, we have several things. First of all, we have a reversible process. So reversible PV work, we should have W reversible equals to negative final minus initial. So final is the volume of liquid, initial is volume of the solid, PdV. Now your pressure is constant, so we can take that out to be negative P and volume liquid minus volume solid. Now this process tells us the liquid volume will be minus the solid volume will be a positive number because of density difference. So your overall work will be a negative number. It's going to be small, but a negative number. Right now, if we give you a specific value for the density and mass, you can actually calculate what's the work that's being done. Yes?
Your integral is going from solid to liquid, but then after...
It's liquid minus solid, right? So here we have liquid minus solid. Final minus initial.
Oh, sorry.
Right, so, and again, like, ask yourself again, what is the physical meaning of this negative W? It tells you your system is doing work on its surrounding because through the melting process, its volume is expanding. And that's the first part. Well, what about Q? So Q here at constant pressure, that's just equals to your melting, which is given. And this is a positive number. And that positive Q means through the melting process, your solid benzene is absorbing heat from the surrounding. All right. And taking together, we have delta U equals to W reversible plus QP. Now, we don't have the number here, but we know this is going to be a very small number for this melting process. The volume change is quite small comparing to the heat transfer. So your delta U will also be a positive number. And your delta H, well, at constant pressure, we can quickly make the link. Delta H equals to QP, which is equals to Q melting, which is a positive number. All right, now we can ask you this question by different ways, right? For example, if we have a multiple choice problem saying like, okay, now considering a reversible melting of benzene solid to liquid, how is your internal energy change throughout the process? And you can say, okay, So do this derivation, and delta U is a positive, so my internal energy is increasing. Yeah.
Can you repeat why QP is equal to Q melting?
This one, that's just true.
Oh, it's just
Yeah, just for this process, it's just Q melting, yeah. Okay. Next one is a very related question, so I'm gonna go a little bit faster. So now instead of benzene, now we are talking about water, which is ice melting to liquid water. And well, because of hydrogen bonding in liquid water, we have the density of your solid water actually smaller than the density of your liquid water. So that tells us my volume of my solid water is larger than the volume of my liquid water. And also the melting is still a positive number. So this processes, we have W reversible. Again, it's the same thing. We have V solid, V liquid, PdV. And doing that same calculation, we have VL minus Vs. But now this number becomes a negative number because your liquid volume is more dense than your solid ice. And this whole thing, the work that's being done becomes a positive number. So again, what does the positive work mean? Positive work means the surroundings doing work on your system. It is contracting. And we have Q larger than 0, which is given here. And obviously your delta H equals to QP will be larger than 0. Your delta U equals to Q plus W. Now both of them are positive, and it's going to be a positive number. All right. The next question is slightly more challenging. I will give you some time to work on it, and I'll stop talking and just work it on my own notes, and then we'll come back and compare our answers with you. So this one, imagine a reversible adiabatic expansion of a perfect gas. All right, so let's work on this together. I'll just write on the board, and you can work it on your own. We'll compare later. How are we doing here? So let's just quickly check our answers together. First of all, it's an adiabatic process. And again, when we're working on this process, just when you're reading it, just write out what each term means with respect in a format of an equation, right? So reversible means you can use W reversible equals negative PDV. Adiabatic tells you that's Q equals to 0, dQ equals to 0. Expansion tells you final volume is larger than your initial volume, and a perfect gas. And what does that mean? We may not end up using everything in there, but just like write it out so you have it in your hand. Now, the adiabatic process, your heat transfer is pretty straightforward. That's just 0. There's no heat transfer between your system and surrounding. But in this process, we can calculate our delta U by looking at the equation here for a perfect gas, which is this one, right? So you have du equals to Cv dt, and you take integral on both ends. You can write out it to be the integral of Cv dt. And the key here to answer whether your delta U is positive or negative becomes how your temperature change in the reversible adiabatic expansion of perfect gas. And that's the example we did at the beginning of today's class. We end up having this relationship here. And what it means is when your gas is expanding, its temperature will drop. All right, and the taking together what we have is delta U is going to be a negative number because your final temperature is smaller than your initial temperature. You can also approach this problem by a different way. So right now I'm using the delta U version. So we start by looking at the internal energy and derive that work becomes a negative number using the first law of thermodynamics. But if you want to use the W reversible of negative PDV, you can also work on it. It's expanding, right? So your change of volume is a positive number. And because you have a negative in the front, well, your work reversible is likely to be a negative number. You can use the first law of thermodynamics reversely and get the same result, that your delta U is negative. So that's one of the charms of thermodynamics. You can always check your answer to make sure it is correct. And delta H then becomes pretty straightforward. We're using the same kind of relationship, right? So your delta H equals to Cp dt, or dH equals to Cp dt. Taking integral on both ends, you have Cp times T final minus T initial. And we know final temperature is lower than your initial temperature. That's a negative number. All right? Yes?
So the reason you can't use those two bottom equations is because it's not constant temperature?
These two?
Yeah.
Yes, the temperature is not constant, so those doesn't apply.
And then the reason, so for Cp and Cv, even though those are defined at constant pressure and constant volume, it's not that we usually use those in this situation, it's quantities that are useful in the situation of closed system.
Right, so Cp and Cv are defined at those specific processes. Remember, in our original definition of heat capacity, you can define it at any processes, right? You can have a combination of, well, non-constant pressure, but half the pressure, and you can calculate Cp. But we don't typically use it. It's just because constant pressure and constant volume heat capacities are very useful in thermodynamics. That's why they're here.
So the situation we can use them in is closed system with reversible Q or only.
Mm-hmm. All right, next up, we have reversible, oh yeah.
I have a question on the last one. When you were calculating the work in the purple there, once you got to the integral, how did you know that, like, the volume, the final volume be larger than your initial volume? How could you, like, make that jump?
Oh, because it's called it's an expansion, so your final volume is larger than your initial volume.
Okay, I was looking at the integral, and I can see that you could take the M and the R out, but the T is still changing, and so is the D.
It's still changing, yes, but the take-home message here is when you're looking at, well, actually, I think I'm taking it too far to just looking at the integral. If you just look at dW, so at every step, even if your pressure might be changing, it's still going to be a positive number. But your volume is always expanding, right? So at every step, your volume is increasing. So this one is positive, this one is positive, so this whole thing is a negative number. All right, so taking the integral, just add them together. We didn't end up with an actual result or like a formula, but you have an idea about that. Must be a negative number.
Is the volume and the pressure both increasing?
Yeah, so your pressure and volume are both positive numbers in the process.
So if you could find that out just from the W equals PdV, is it necessary to substitute it with nRT?
It's not. I mean, there are two different ways to do it,
Oh, okay.
right? But both of them gives you the same result. That's a take-home message.
So why do we use CP for calculating delta H?
Well, just keep in mind, CP is, you can think about it as a number. All right, so in this case, we can use it because for ideal gases, you have the relationship of dH over dt equals to CP, So CP, you can imagine that to be a number or a coefficient. It was measured at constant pressure, but you can use it at different scenarios. All right? And in this case, you can actually write this out. So CP equals to CV plus NR for ideal gases. Yeah.
We can always assume that volume and temperature are inversely related.
No, this is only for this relationship, which is, well, perfect gas, adiabatic, closed system, constant CV, reversible PV work only.
Okay.
All right, so that's a dangerous claim. It's not always like that, but for these scenarios, yes. Okay. Next up. Next one is a reversible isothermal expansion of a perfect gas. So isothermal, that tells me dt equals to 0. Expansion tells me V final is larger than V initial of a perfect gas. All right. So now it's an isothermal processes involving perfect gas. So some of the terms are become very obvious. So your delta U equals to 0, delta H equals to 0 because of perfect gas and isothermal. And then you have the work and heat that comes to play. Now in here, we have reversible process, so we can use WREV equals to negative V initial over V final PdV. And in this one, we can actually pretty straightforward to solve it. You have V initial, V final, negative nRT over V dV equals to negative nRT times ln V final minus ln V initial. Now this one inside the bracket, your final volume is larger than your initial volume, and that is a positive number. So this whole thing is a negative number. All right, so your whole thing is a negative number, meaning in this process, it's an expansion. Your system is doing work on its surrounding. And, well, the heat becomes quite straightforward. So your Q equals to delta U minus W, so it must be a positive number. So even if it is isothermal, because it is expanding, your system is doing work on the surrounding. So keep your first law of thermodynamics holds, you must have heat transfer equals to positive. All right. Next up, we have our adiabatic expansion of a perfect gas into vacuum. So this one is just our Joule experiment setup. So it's adiabatic, so dq equals to 0, q equals to 0. expansion tells you V final larger than V initial of a perfect gas, and you have that set of equations for perfect gas. So in this case, we have Q equals to 0. And remember our Joule experiment setup? We have the perfect gas is expanding into the vacuum. It is by no means doing any work to its surroundings. All right, so your whole container is a rigid container, and in our Joule experiment setup, your work also equals to 0. And note in this case, we want to specify one thing, is that you cannot use that W reversible equals negative PdV because this is not a reversible process, right? Once your gas expanding into the vacuum, it can no longer come back to its initial state. It's not a reversible process, so we can't use that W equals negative PdV. Well, and then you have delta U equals to Q plus W equals to 0. You have delta H also equals to 0 for these processes. Just Q is 0 and W is 0. So consequently, delta U becomes 0, and that delta T is 0, and that gives you Y delta H equals to 0. Yes?
Can you just explain one more time how you got W equals 0?
Well, that's just in the Joule experiment setup. So you can go back and check what we said in our Joule experiment setup. That's the adiabatic expansion of a perfect gas into vacuum.
Okay.
Yeah.
And so you saw that the internal energy is 0, and because it's 0, you can assume the temperature change is 0.
Yeah.
And then you can assume that temperature.
Yeah. Because for ideal gases, your internal energy is only dependent on temperature.
So temperature must not be changing.
Yes. And we have 3 more examples to do together. We have also our Joule-Thomson experiment. So this one you can try it yourself. I mean, I'm just telling you this one is the same as our Joule-Thomson experiment, and try it yourself and find out what the relationships are. And let's do this example together. This one is called a reversible heating of a perfect gas at constant pressure. So we have T final larger than T initial at constant pressure. So that means our delta H equals to QP. It's reversible, so we can use W reversible equals to negative PdV. And it's a perfect gas. You know what to write for perfect gas. And what about the relationships? The first thing, we already have it here, right? By just reading the question, we know what delta H is. And it equals to QP. And how do we find out delta H in this case? Well, it's a perfect gas. So we can write out T initial, T final, CPT dt. And now we know the final temperature is higher than your initial temperature, so this must be a positive number. All right, so we already have our delta H and QP. Delta U is the same thing, right? Your temperature is increasing, your internal energy must be increasing. Or if you want to write out the integral, you can write it out as well. But the work is a different story. Now we don't know what's the relationship between work and QP because both your delta U and QP are positive, but we don't know what exactly is the number for that W and Q. So we can calculate our work reversible equals to negative V initial to V final PdV. Now it's at constant P, so we can take that P out. I just want to find out what my V final and V initial is. So in this example, we have PV equals nRT. And we know this process is like the temperature is going up, the volume is kept at constant. So this one is going to be a positive number. Right, so volume equals nRT over P, and your P final is larger than, your T final is larger than T initial. N, R, and P are all constant, so your V final is larger than V initial, and your work will become a negative number. All right, and keep in mind, what's the physical meaning of these terms here? When we have positive QP, what we're saying is your surrounding is transferring heat into your system. And when you have a negative work, it means your system is doing work on its surrounding. So that's just the essence of our entire chapter 2. I have one more example you can try it on, but I don't think we've done these examples, and try it on and compare it to the annotated notes and know how to do these problems. And again, two things that we can test you on. One of the things is, instead of just directly saying it's reversible heating of a perfect gas at constant pressure, we could give you something like a Joule experiment setup or a Joule-Thomson experiment setup, or the analog of this kind of experimental setup. You want to translate that experimental setup to the thermodynamic concept, like adiabatic, isothermal, isochoric, and etc., and then connect those thermodynamic concepts to specific equations and find out how does these more abstract terms change throughout the process of any processes. All right. And our next lecture, we will start talking about entropy. So our next Monday, Wednesday, we'll talk about entropy. We'll see how far we go on Friday. And your first midterm exam is the Monday after next week, and it's going to cover everything through like next Wednesday.